Conformation of cyclohexane, axial and equatorial hydrogens. Cyclohexane can exist in a conformer called chair, in which at each carbon center the C-C-C bond angle is 111 degrees. This is very close to the tetrahedral bond angle of 109.5 degrees. Hence, there is no tetrahedral bond angle strain in cyclohexane. There is perfect staggering between all the C-C single bonds, and hence there are no eclipsing strain either. In cyclohexane chair conformer, 6 of the 12 hydrogens have an orientation called axial, and the other 6 have an orientation called equatorial. By ring flipping, involving rotations around the C-C bonds, one chair conformer is converted to another chair conformer. In this process, every axial hydrogen in the original chair becomes an equatorial hydrogen, and every equatorial hydrogen becomes an axial hydrogen. Conformational analysis of cyclohexane, ring flipping. During ring flipping, a series of intermediate conformers called half chair, twist boat, boat, twist boat, and half chair with various energies and stabilities are formed. Ring flipping, that is, the conversion of one chair form to another chair form, involves an energy of 12.1 kilocalories per mole. At any time, nearly 100% of the cyclohexane molecule exists in the chair conformation. Conformational analysis of methylcyclohexane. Methylcyclohexane can exist in two chair conformations. The one in which the methyl group occupies an equatorial position is more stable by about 1.7 kilocalories per mole than the other in which it occupies an axial position. Ring flipping would result in the conversion of one to the other. In conformer B, the hydrogens of the axial methyl group is within 190 to 200 picometers of the axial hydrogen at C3 and C5. This distance is less than the sum of the van der Waals radii of two hydrogens and causes steric or van der Waals strain in conformer B with methyl in the axial position. This strain is also referred to as 1,3 diaxial strain. In conformer A with methyl group in equatorial position, there are no steric strains. The degree of strain due to a substituent on the ring depends on its size. The relative degrees of 1,3 diaxial strain in kilocalories per mole due to different substituents are given below. Cyclohexane with a fluorine substitution experiences less strain than a chlorine or bromine substitution, which in turn experiences less strain than a hydroxy substitution, which in turn experiences less strain than the methyl substitution, etc. Cis-trans stereoisomerism in substituted cyclohexanes. Because of the rigidity of the cyclohexane systems, they have two faces, a bottom and a top. Due to this, substituted cyclohexanes exhibit stereoisomerism. In cis-1,4-dimethyl cyclohexane, where the two methyl groups are on the same side of the cyclohexane system, they have a cis-stereoisomeric relationship. Note that ring flipping does not change the cis relationship between the two methyl groups. Cis-1,4-dimethyl cyclohexane can be represented as a flat structure. Two solid or wedged bond lines are used between the ring carbon and the methyl carbon to indicate the cis relationship. Cis-trans stereoisomerism in substituted cyclohexanes. In trans 1,4-dimethyl cyclohexane, where the two methyl groups are on the opposite sides of the cyclohexane system, they have a trans stereoisomeric relationship. The trans 1,4-dimethyl cyclohexane can be represented as a flat structure as shown here. The thick bond line between the ring carbon and the methyl carbon indicates the methyl group that is up. The wedged line is used to indicate the methyl group that is down. The cis-1,4-dimethyl cyclohexane and trans 1,4-dimethyl cyclohexane are stereoisomers of each other. One cannot be converted to the other due to ring flipping. The cis and trans stereoisomers have the same carbon bond connectivity but permanently differ in the orientation of the substituents in three-dimensional space. Conformational analysis of disubstituted cyclohexanes. Cis-1,4-dimethyl cyclohexane can adapt either of the two conformers, A or B. In both conformers, one of the methyl groups is in an equatorial position, the other in an axial position. Hence, both suffer from 1,3-diaxial strain and have the same stability and energy. Trans 1,4-dimethyl cyclohexane can adapt either of the two conformers, A' or B'. In conformer A', both methyl groups are in an equatorial position and is free of all strain. In conformer B', both methyl groups occupy an axial position, hence suffer 1,3-diaxial strain. Conformer A' will be favored over B'. At any time, more than 95% of the molecule will adapt conformer A'. Between cis-1,4-dimethyl cyclohexane and trans 1,4-dimethyl cyclohexane, the trans is more stable since in one of its conformers, A', it is free of all strain. Conformational analysis of disubstituted cyclohexanes. Cis-1,2-dimethyl cyclohexane can adapt either of the two conformers, A or B. In both conformers, one of the methyl groups is in an equatorial position and the other in axial position. Hence, both suffer from 1,3-diaxial strain and have the same stability and energy. Trans 1,2-dimethyl cyclohexane can exist in either of the two conformers, A' or B'. In conformer A', both methyl groups are in equatorial position and free of all strain. In conformer B', both methyl groups occupy an axial position and hence suffer 1,3-diaxial strain. At any time, more than 95% of the molecule will exist in conformer A'. Between cis 1,2-dimethyl cyclohexane and trans 1,2-dimethyl cyclohexane, the trans is more stable since in one of its conformers, A', it is free of all strain. Conformational analysis of disubstituted cyclohexanes. Cis 1,3-dimethyl cyclohexane can adapt either of the two conformers, A or B. In conformer A, both methyl groups are in equatorial position and is free of all strain. In conformer B, both methyl groups occupy an axial position and hence suffer 1,3-diaxial strain. Trans 1,3-dimethyl cyclohexane can adapt either of the two conformers A' or B'. In both conformers, one of the methyl groups is in an equatorial position, the other in axial position. Hence, both suffer from 1,3-diaxial strain and have the same stability and energy. Between cis 1,3-dimethyl cyclohexane and trans 1,3-dimethyl cyclohexane, the cis is more stable since one of the conformers that it can adapt, A', there are no strains.